Hi folks, in this video we're going to take a look at the idea of solving a polynomial inequality. So in the last one we saw how to solve linear inequalities, and we did that in a very similar way to solving linear equations because we could isolate the variable. Okay, as soon as we get to a polynomial, or in this case here quadratic inequality, we have the same problem as we had before with quadratic equations. You can't solve for x explicitly. Okay? So think about what we did, is we used the fact that if we were looking for when this equation was, or this expression was equal to 0, well, we tried to write this expression as the product of two other expressions. So here we did that by factoring. So x minus 3, x minus 1, okay, equals 0, and we use the idea that the only way for this whole expression to be 0 was if one or the other was equal to 0. So either x minus 3 had to be 0 or x minus 1 had to be 0. Okay? But here we're trying to solve for when it's greater than 0. But I want you to think about a polynomial function. Any polynomial function, the fact that it has this continuous property, okay? The question is, when can a polynomial function ever change sign? And we realize that the only time a polynomial function can change sign is if it crosses the x-axis. So here, crosses the x-axis, goes from negative to positive. Here, crosses the x-axis from positive to negative. Here, crosses the x-axis, goes back from negative to positive. Okay? In other words, the only places where this polynomial can change sign is at an x-intercept. Okay? Now be careful, it doesn't have to change sign at an x-intercept, because if you have, say, a 0 of order 2, it might be equal to 0 here, but doesn't actually change sign. But if we're looking for where it changes sign, that can only happen at an x-intercept. And the other thing I want you to think about is that think of all the points in between those two x-intercepts. If there's no other x-intercept in between them, the sign of the function has to always be the same. So as soon as I can show that one point has a positive y value, every other y value in this interval has to be positive. If I can show that one y value in this interval is negative, then it means all of them have to be negative. So these are the ideas that we're going to use. So let's take a look at this example here. Let's think of x minus 3 times x minus 1 as a parabola. Okay, if I were to draw a quick sketch, okay, I know it crosses the x-axis at 3 and at 1, or sorry, at 1 and at 3, and it's an upward-facing parabola because the leading coefficient would be positive. Well, I can draw myself a quick sketch, and I realize I can read right off my sketch where it's going to be positive and negative. Okay, it's going to be greater than 0, well, when x is less than 1, or when x is greater than 3. Now, because my inequality here is greater than 0, it has to be strictly positive. I'm not going to include 1 and 3. Whereas if it had been greater than or equal to 0, I would have included those. So here, just by quickly drawing the graph, I can write the answer as x having to be an element of, well, negative infinity to 1, not including 1, and union 3 to positive infinity. Okay, so not surprisingly, we have an inequality and we have infinitely many possible solutions. Okay, but here what we're using is the exact same methods we did to solve a polynomial equation, which is to factor it and you work with the zeros to help us determine our answer. Now, one thing that I want you to keep in mind is that notice what I needed to have on one side of the equation. As when you're solving polynomial inequalities, this idea only works if I've got 0 on the other side of the equation. Okay, so let's look at the example that's in the notes that are either the notes you've gotten or that you'll be receiving. Okay, so here we've got our polynomial inequality question. So here it says that this P at X models the profit of a company over a 10-year period, and it asks determine the times at which the company is operating at a profit and the time it operates at a loss. So in other words, what we're looking for is when is P greater than 0, operating at a profit, operating as a loss, meaning the profit is less than 0. They're actually losing money. Okay? So let's write P at X here. Okay, and that's okay. Right off the bat, I notice that I've got a common factor. So to help myself out, I'm going to start by factoring out the common factor. Okay, and remember what we talked about earlier. The only place this function can ever change sign is at an x-intercept. So my goal is to find the x-intercepts of this function. Okay, now here we see a quartic. Notice it's missing the x squared term. I can't really think of any traditional factoring methods to use here, so I'm going to use the factor theorem. So we'll start again with the simplest factor of 16, which is 1. Okay, so what do we have here? We've got 1 minus 5 is negative 4. Negative 4 plus 20 is 16, and 16 minus 16 is 0. So we lucked out here because the first one we tried gave us the 0 we needed. Okay, so now we know that x minus 1 is a factor of the polynomial. Okay, so let's do our division in order to find the remaining factor. So 1, okay, so 1, negative 5. Be careful here because there's no x squared term, so you have to add the 0x squared. And we got 20 and negative 16, so let's just perform our synthetic division. So 1 times 1 is 1, so that gives me negative 4. 0 plus negative 4 is again negative 4. This gives me 20 minus 4, 16. And then here, negative 16 plus 16 is 0. So as expected, the remainder is 0. So that means P at X can be written as 2 times, don't forget the 2, we really should put that in there. It is one of the factors. Our original factor of x minus 1. And now the other factor here, this will be our cubic, x cubed minus 4x squared minus 4x plus 16. Okay, and so now we'll see if we can keep going. And this is where, well, lo and behold, looks like the grouping might work in this one here. So let's give it a try. So take out the x squared, we're left with x minus 4. Remove a negative 4, and we're left with x minus 4. Okay, so we keep going on until we factored it completely. So x minus 4, and here we're left with x squared minus 4, which of course is a difference of squares. So this actually factored out quite nicely. This just becomes x plus 2, x minus 2. Okay, so remember what we said. We want to determine in this case here both positive and negative, but that's all going to rely on where the zeros of this polynomial are. So I'm not even going to bother with the y-axis here because I don't really care about how high or low it goes. The only thing I care about is when it's positive and negative. Okay, so I notice in order that my zeros are, well, negative 2 is the smallest. Okay, then the next one would be 1, the next one would be 2, and the last one would be 4. Okay, now if I were to multiply this out, I can see that, or if I go back to my original equation, I can see that the leading coefficient is positive. So this is going to be a quartic, and I can just draw myself a quick little sketch of that graph. So I don't have to actually test anything in between. I know that if there's no 0 between negative 1 and 2, it's going to have to remain negative the whole time. So right from here, I can read off my answer. Okay, there is one little thing that you might want to think about though. What are we talking about in this question? Okay, P at X represents profit, okay, over a 10-year period. Okay, so X represents time. That means we're starting off at x equals 0. We're not interested in anything before 0. And we're stopping at x equals 10. We're not interested in anything past 10. So when we're giving our answer, you have to be sure to take into consideration the natural restrictions, so time being positive, and then the given restrictions that we're only interested in the first 10 years. Okay, so now we can give our answer. Okay, when are they operating at a profit? Okay, well, it looks like they're operating at a profit between year 1 and year 2. Okay, now in this case here, at 1 exactly, looks like they're breaking even, meaning the profit is 0. They haven't made money, they haven't lost money. Same thing at 2. So it doesn't make sense to include 1 and 2 here, because they're not actually making a profit. They're not losing money, but they're not making money. Okay, and it looks like they're also making money after year 4. Okay, so again, we won't include 4. Okay, but at year 10, well, this is still positive. So the profit is positive. They are making money. So here I would include 10. Okay, so now let's look at the loss. This is where the profit is 0. So we see that at year 0, it starts off at a loss. So again, at year 0, they are losing money, so I would include that in my answer. But at year 1, while they're not losing money, they're not making money. So we have to use a round bracket. And we see that they're also losing money between years 2 and 4. And again, as before, we don't include the endpoints. Okay? So just to review how we solve these inequalities, okay, we do essentially the same thing as we did for solving a polynomial equation. Okay? You try to factor the expression, and you use the fact that those zeros that you find are the only places where the function can change sign. Okay? And you use the fact that you can easily sketch the graph once you know the zeros, the leading coefficient, and the degree. Okay, that's it for now.